Section 11.5, evaluating definite integrals. Here are 5 properties of a definite integral. Just to go over these briefly, number 1, if the limits of integration are the same, the answer is going to be 0. You haven't moved anywhere on the x-axis, so the value of the definite integral is 0. And number 2, if you interchange the limits of integration, you're going to get the opposite of the value of the original definite integral. And number 3, if there is a coefficient that precedes a function, you're able to take that coefficient out front and put it in front of the definite integral notation. If a situation arises where it's of benefit to you to rewrite a single definite integral as a sum or difference of 2, then you're able to do that based on that property. And finally, number 5, if a situation arises where you're looking at the integral over the interval from a to b, if for whatever reason you have to break up this interval into 2 intervals, a to c and then c to b, you're able to do that. And this will really play an important role when we actually look at the area that is being bound by various curves as we proceed through the rest of chapter 11. So now we're going to look at some examples to illustrate these properties and to look at what is called the method of substitution for the definite integral. Exciting, fascinating stuff. Let's get to it. So what we're going to do now, example number 1, is use the method of substitution for definite integrals. And what we have to do is change the limits of integration in order to accomplish that. So here's what we're going to do. The first part is to determine what you want u to be equal to. So I encourage you to review what we already have discussed in section 11.2. All right, using u substitution to evaluate an indefinite integral. Now we're going to use u substitution ultimately to evaluate a definite integral. So do we remember that process? If not, I'm going to go ahead and show it to you now. So if possible, you're going to try to find an expression that's part of the larger expression that's 1 degree greater than some other piece of this puzzle, okay? So in this case, we're going to look at u being equal to 2x cubed minus 1. And again, that's because this expression is 1 degree greater than some other variable expression making up this entire function. What we're going to do now is we're going to take the derivative of both sides. So we really get 1 du here on the left, and then on the right we get what? We get 6x squared with respect to x, so 6x squared dx. And now we're going to do the same thing that we again did in section 11.2. We're going to divide both sides by 6, which really gives us 1/6 the u on the left. All right, here's where it's going to change now in terms of the process because we're now looking at definite integrals. So here's what I recommend. When you show your work, draw 2 arrows just like that. All right? And now what you're going to do is, if there is a coefficient preceding du, in this case there is 1/6, write that down right about there. Then draw your integral symbol. And at this point, we have to change our upper limit of integration and our lower limit of integration based on what u is now equal to. So here's all you have to do to accomplish that. Let's start by looking at our original lower limit of integration. It's 0. So this is x equaling 0. We now want to make this in terms of u. So all you have to do is substitute in this 0 into every x that u is equal to. So put this 0 into this x. What's 0 cubed? It's 0. 2 times 0 is 0. 0 minus 1 is minus 1. So now u is minus 1. When x was originally 0, you're now going to get u equaling -1, your new lower limit of integration. Okay, let's determine our new upper limit of integration. Same process. Go to your original upper limit, it's 1. Plug it in, right here. So plugging in 1 right here would give us 1 cubed, that's 1. 2 times 1 is 1. Excuse me, 2 times 1 is 1. Jeez, this is why you do not smoke crack before you do these online YouTube videos. Okay, moving on. So 1 cubed is 1. 2 times 1 is 2. 2 minus 1 is 1. So we're going to put a 1 right there. And now let's see what else we have. I tell you what, I'm going to break this down in a diagram, at least this first example, for everybody. So look what we have here in our integral. Our original integral, x squared and then dx. Okay? Look what we have here, x squared dx. That's nice. Also, look what we have. We have 2x cubed minus 1 in our original integral. And then we have a 2x cubed minus 1, of course, down here. All right, so what can we do with that? Well, here is what we can do with that. Use substitution. This entire expression is now just u. This entire expression, everything, x squared dx, is now just du. The only thing we're missing is this. Do not forget this, of course. All right? This exponent 4 still remains and becomes a part of our new integral. All right, let's rock and roll and finish this thing now. So, what do we get? Well, the 1/6, that's your c value, that remains in front. And then we now integrate this, so that would give us u to the, what? 4 plus 1, 5, divided by the new exponent 5. Then we're going to look at evaluating this over the interval from -1 to 1. All right, so we could either leave this 1/6 out in front and not multiply it by the 1/5, which is what this is, which would give us 1/30. We could do that, or we could just leave it like it is. I'm just going to leave it like it is. And then wherever I see a u now, I'm going to first replace it with the upper limit of integration, just like that. Then I'm going to remember to do what? To subtract off whatever we get for the lower limit of integration, which is going to be represented by what? The quantity of -1 to the 5th all over 5. And then what do we get? Well, we get 1/5 minus a -1/5. And so, what does this ultimately give us? 1/6 times, a negative times a negative is a positive. So 1/5 plus 1/5 is 2/5. And we get 2/30, which of course, finally, gives us what? Reduce 1/15. There you go. First example under our belt. Let's move on to example number 2. Keep this fun train rolling.